Hello, good afternoon, students. Hope you're doing well. Be at home and stay safe. Now, yesterday I have sent a video based on the applications of Magic Tea. I would try to review it again, and I'll be discussing the applications of Magic Tea. The first one is Magic Tea, how it behaves as an impedance bridge. So let us have a look at the diagram. Okay, this is the diagram of a Magic Tea as an impedance bridge. You can look at the four arms. We know that Magic Tea is a four-port device with the four arms. So port 1 and port 2, these are called the collinear ports. And port 3 is the H arm where we have connected a microwave source here. And port 4 is the E arm where a microwave detector is connected. To port 1, a standard variable impedance is connected, which is Z1. And at port 2, there is an unknown impedance Z2, which we have to compute what is the impedance at that port, that is port 2. So we need to compute the value of Z2. So in this impedance bridge, now we'll be applying certain properties of Magic T in order to solve it. And if we, so as you can see in the diagram, the microwave source is connected to which arm? That is port 3 or the H arm. Now, as per the property of the Magic T, which has been earlier discussed in the previous classes, we have seen that when input is applied to port 3 and there is no input from port 1, 2 or 4, input is only applied to port 3, it gets equally divided between 1 and 2 and there is no output measured at port 4. So let this incident component, because it is port 3, let the incident component be A3. So A3 is present and A3 gets divided equally among port 1 and port 2. So the value available at port 1 and port 2 is A3 divided by root 2 and A3 divided by root 2. So these coefficients are assumed as reflected components from, or incident components from port 3, and we can call it as what, M1 and M2. Let it be M1 because M1 is the value going into port 2 and M2 is the value going into port M1 is the value going into port 1 and M2 is the value going into port 2. So M1 is equal to A3 divided by root 2. M2 is also equal to A3 divided by root 2. Now when M2 is equal to A3 divided by root 2 is fed as an incident waveform to port 2, there will be some reflections from port 2. Let that reflected component be M4. Now this reflected component M4, because now this serves as incident from port 2. So whenever there is some incident signal from port 2, it gets equally divided between port 4 and port 3 and there is no output at port 1. That's why the name Magic T. We have already seen in the previous class also. Whenever there is an input from port 2, there is no output at port 1, but equal in magnitude output is available at port 3 and port 4, and port 4 output is 180-degree out of phase of the output which is appearing at port 3. The reflection coefficient of port 2 is K2. And we know reflection component is the ratio, or reflection coefficient is the ratio of reflected component to the incident component. So reflected component for port 2 is M4 and incident component is M2. So the ratio of M4 divided by M2 is equal to K2. And M2 is nothing but A3 divided by root 2, because that's how we got it. Okay. Now this M4, which is the reflected quantity coming from port 2, gets divided equally between port 4 and port 3, but the output at port 4 is 180 out of phase, so we will get minus 1 divided by root 2 M4 over here and plus 1 by root 2 M4 over here. Now we are concerned only with the component which is going into port 4, so I will say M6 is equal to what? Minus 1 by root 2 into M4. Okay. Now so this part is done. Now when there was an incident component for port 3, it got equally divided in port 1 and port 2. Now the quantity which is coming into port 1 is your M1, that is A3 by root 2. Now when there is an incident thing, there will definitely a reflected component when it is not properly matched, as we already know. So let's say M3 be the reflected component. The reflection coefficient K1 will be the ratio of reflected component to incident component. So what is the incident component? M1. And what is the reflected? Sorry, the incident component is M1 and the reflected component is M3. So K1 is the ratio of M3 divided by M1. And M1 is nothing but it's A3 divided by root 2. Okay, so this M3, which is the reflected component of port 1, now that also gets divided between port 4 and port 3, equal in magnitude and same in phase as well. So equal in magnitude and phase. So the amount which is going over here, let's say that component be denoted as M5. So M5 is equal to 1 by root 2 M3, and we have not shown the component which is appearing here because that is not of our interest as of now. So even that will be also equal to what? 1 by root 2 M3. Okay. So now if you look at port 4, there are two things, waveforms coming here. M5, which is 1 by root 2 M3, and M6, which is minus 1 by root 2 M4. So the total value of the waveform or the signal power available at 4 is the summation of M5 and M6. So if we look at the expression, we can say that total signal reaching the detector, which is connected at port 4, M is equal to M5 plus M6. And as I mentioned earlier, M5 is 1 by root 2 M3 and M6 is minus 1 by root 2 M4. M3 can be represented in terms of reflection coefficient, as I have discussed here. So reflection coefficient K1 will be equal to reflected component by incident component M3 divided by A3 divided by root 2. So M3 is equal to K1 into A3 divided by root 2. That's what is used here. K1 into A3 divided by root 2 minus 1 by root 2. Similarly, M4 can also be represented in terms of K2. So K2 into A3 divided by root 2. So when we solve, and we can write M is equal to 1 by 2 A3 whole into K1 minus K2. K1 minus K2. So this root 2 gets multiplied, and root 2 into root 2, root 2 into root 2. So we have 2 over here, 1 by 2 A3. Okay. Now what is A3? A3 is the input which is fed from port 3. So A3 is the input which is fed from port 3. So it cannot be 0. It cannot be equal to 0. So A3 is not equal to 0. Since A3 is not equal to 0, in this expression we can say K1 minus K2 is equal to 0 or K1 equal to K2. What are K1 and K2? Reflection coefficients of the two ports, port 1 and port 2, which are terminated with impedances Z1 and Z2. So we can write the reflection coefficient in terms of impedances. So K2 can be represented. We know reflection coefficient is ZL minus Z0 divided by ZL plus Z0. The well-known formula we have used a number of times. So we'll substitute here. So in place of K2, I'll write Z2 minus Z0 divided by Z2 plus Z0, and in place of K1, it is Z1 minus Z0 divided by Z1 plus Z0. By using componendo and dividendo, we can just solve it, and we get Z1 is equal to Z2, and Z2 is R2 plus JX2, Z1 can be written as R1 plus JX1, and hence we have R2 is equal to R1 and X2 is equal to X1. So the detector will show null deflection only when the magnitude and phase of the unknown impedance Z2 is equal to that of the standard variable impedance Z1. Thus, the impedance can be measured using magic tape. So this is an important application of magic tape. Magic tape acting as an impedance bridge. Under the balance condition, we need to find out the value of the unknown impedance which is connected to